Okay, so today we're going to work with special exponential functions that have like their own like little formula that y equals a times b to the x power is still the model that it's based around. So in the we're going to work with exponential growth and exponential decay. So I want you to highlight first of all right here this very first sentence, because again this is going to be important that you understand what all the parts of these special exponential growth functions model, okay, represent. So in the exponential growth and decay formulas, y is the final amount, a is the original amount. Well, that kind of looks like our model, doesn't it? Y equals a times. R is the rate of growth or decay as a decimal. So if they say, like yesterday in our problem when there was a 20% increase, they didn't show it as a 20 in the b value. They didn't show 120. They showed 1.2, its decimal name. So in this one, it would be 1 plus whatever the percentage of growth or decay is as a decimal, and then we would have our 1 point something, okay? Or it would be less than 1. And t equals time. So remember I said sometimes the x value in the exponent is a t instead of an x. So basically, the things that are different are that kind of replace the b value in our model. Let's write our model up here. Our exponential model really goes like this. Y equals a times b to the x power. We're not really veering away from that. We're just now using it for particular things. So in our y equals a times 1 plus r raised to the t power, that's our exponential growth one. And the 1 plus r is really the what? From the model? The b value. And the t is really the x from the model, okay? And for the exponential decay, we have y equals a times 1 minus r. So the 1 minus r is really the b value again, and the t is the x value. Okay, so let's take a look at, oftentimes here's the reason that students don't get their papers stamped for this assignment, is because they don't hear me on the part that there are two answers for these. Because in this particular one, it's probably a good idea if we highlight this. Write the exponential growth function to model the situation. That's one of the answers. The exponential function that still has the y in it and it still has the t in it. Okay? So in other words, we could figure out the final amount given what amount of time there is for any particular situation. So the model, and then it says, then find the population. So then is the second answer. Now use your model, given the information you have about either the final amount or the time, and get your final answer. So in this one, here's an example of an exponential growth. The population of a city is increasing at a rate of 4% each year. In 2000, there were 236,000 people in the city. So in the year 2000, that's like our t value of 0. In fact, let's write that right here. Let's put that in there. That this really means right here, t equals 0. That's our starting point. No time has gone by. We're starting in the year 2000. And there are 236,000 people in the city. This would be our A amount right here. This is our A. What does it start at? So what is the population in that starting year 2000? And then since it's increasing at a rate of 4%, that means we need the growth one. And we need to change our R value to a decimal. So notice how right here, R is a 0.04 to represent our 4%. So when we're doing the model, we have to use, first of all, the exponential growth model. We substitute our A value in. We substitute our R value in. Those are the only two substitutions made. And we say this, would you circle this? This is the model for this city's population increasing at a rate of 4% each year, starting in the year 2000 with 236,000 people in it. It's not Valley City, is it? Nope. Okay. That's the first answer. The second answer is now it says find the population in the year 2009. So you have to figure out what T is. So T equals 9. Why? Why does T equal 9?
Because it's been a time. Years.
Yeah, that's how many years has gone by since the year 2000, the time when time was 0, to 2009. 9 years have passed. So we put a 9 in for the T value. So notice the only new substitution is that right there. The 9 replaces the T. And now we get our Y value, and because it's people, they round it to the nearest whole number. And we would say, okay, here's our second answer. So 2 answers for these problems today. Okay, let's look at one where there is decay going on. The only difference should be is we're subtracting the percentage as a decimal away from 1 instead of adding it to it. So everything else should stay the same. So we have in the year 2000, that's our T equals 0, rate of 6%. This one is decreasing at a different amount, so 6% is, as a decimal, is 0.06. And what's the A value? 35,000. That's what the population is when? At the start. Okay? And then it says, write an exponential decay function to model this situation. Answer 1. Then find the population in 2012. Answer 2. 2 answers again. So answer 1 is right here. Again, it has the Y and the T in it. Answer 2 is right here. Okay, let's go practice a couple of our own then. Write an exponential growth function to model the situation. First answer, right there, number 1. Then find the value of the function after the given amount of time. Answer 2. Okay, annual sales of a company are 372,000 and increasing at a rate of 5% per year. So would we use the exponential growth function or the exponential decay? Growth, because it is increasing. There's our giveaway. So we're going to write down y equals a times 1 plus r raised to the t power. We're going to figure out what's our a, because that's what we're going to substitute for. What's our r? That's the other thing we're going to substitute for our first answer. So what's our A? Josh?
372,000.
Yep, 372,000. And what's our R?
0.05.
0.05. Okay, 5% change to a decimal. I don't care about the after 8 right now. We are doing our first answer. Okay? So we are going to say y equals 372,000 times 1 plus 0.05 raised to the t power. All we do is just clean that up. What can we do?
It's 372,000.
1.05?
Yeah.
Yeah, add the 1 and the 500s together. Actually add them. And that's a T. There is our first answer. There's our first answer. The model that says, now, if I say to you, when will their sales be 500,000? You put 500,000 in for Y and you'd solve it for T. If I say to you, what will their sales be after 15 years, then you would put 15 in for T and you'd solve it for Y. So this model works no matter what situation I give you. Now, part 2 says, okay, now you can substitute in and since it's after 8 years, that means we're going to substitute 8 in for the time. And we are going to round this. This is money. So what do we round to with money? Hundredths. Okay, so calculate that out and let's see how much the sales will be for this company after 8 years. Should it be larger or smaller than 372,000? It better be larger. Okay. Who thinks they have it for us?
$549,613.43.
Yeah. Everybody agree with that?
Not if you round to the hundred, it'd be different. I'm guessing you just click times when you got your decimal. Cause when you multiply 1.05 to the eighth,
It's like 1.47.
yeah, and if you round that, but I guess if you.
Okay,
plug
yeah,
just
but if you
plug
don't
it-
round, just put it all in at one time. See if you can figure out how to do that in your calculators. Or in other words, if you want to put in 1.05 and raise it to the 8th power first and get that answer, then does your calculator allow you to just say then times 372,000?
Yeah, that's what I do it, so.
I did.
But you still do time, you don't round in the middle,
No.
you just do the power first and then you go back and multiply. Yeah, that works too. But this is the answer we should get, because we don't want to round in the middle of it, okay? So we're going to say this is answer number 2. Okay, it says write an exponential decay function to model the situation, then find the value after the given amount of time. Again, there are 2 answers. We have this one and then this one. So we have an internet chat room that has 1,200 participants and is decreasing at a rate of 2% per year. So we need the exponential decay one, right, because it's decreasing. So y equals a times 1, subtract the r value as a decimal, raised to the t power. And our a value is what? 1,200. And our r value is 0.02. Okay? So we're writing our model right now. Y stays y, a gets replaced with its value, the r gets replaced with its value, the t stays t. Now we take 2 cents away from $1, what do we get?
Negative 0.0.
No.
Is that negative?
0.9.
It's like $1 take away 2 cents, how much is that?
98.
98 cents, right? Okay. There's our answer number 1. It has a y and it has a t. The model that will work for whatever situation you want to use with this problem. And then problem number 2 says, the second part says after what? How many years? 5 years?
Yeah.
And these are what? Computers? People, okay. So if they're people, we round to the nearest whole, right?
Yep.
Okay. So how many participants are there? 80 how many? 5. There should be 1,085 participants. Can we have part of a person? No. There's our second answer. Okay, exponential growth and decay when you have something increasing or decreasing at a certain percentage. Questions? Okay, let's go to the next side, where we are going to work with a special exponential growth one on this one, and then there's going to be another special exponential decay one on the other. So we are going to highlight in here that we have a special type of exponential growth that involves compound interest, a very common thing in our world. Compound interest. So, would you also highlight or somehow make sure that you can see that wonderful looking, a little bit involved formula that will help us find how much money would be in an account after it was earning compounded interest for a certain amount of time. So all of these things are important that we understand. In this one, it's instead of it being Y, this is kind of like our Y value, this capital A, it's how much is in the, what's the total balance? So again, it's like a Y. P is the original amount. What would that be like in our typical model?
With the starting one?
Yeah, what part of our typical model, Y equals A times B to the X power, would that be? That would be like our little a, isn't it? Okay, and then R, well, we've already worked with what little r is. And then N, this is the part, you know what, you might want to underline this one, highlight it, whatever you want to do. That's going to be new. N is the number of times the interest is compounded in 1 year. So let me give you some examples of how we would have to make a decision for N. If it says it is compounded annually, how many times would that be? Once a year, so then N would be 1. What if it's compounded quarterly?
4.
That'd be 4 times a year, so then N would equal 4. What if it's compounded monthly? 12, then N would be 12. What if they're really generous and they compound it daily?
365.
N would be 365. So according to how many times in 1 year it is compounded, that determines our N value. And then T is still our time measured in years. Okay? So they have an example over there, but we're just going to go right to word practicing a couple of them, and you can use that as your own example to study. Okay? So write a compound interest function to model the situation. Oh, answer number 1. Then find the balance after the given number of years. Answer number 2. Okay, so we have $17,000 invested at 3%, compounded annually. So the first thing we're going to do is we're going to decide what do each of these things represent in our formula. So what would the $17,000 be in this compounded interest formula?
P.
Big capital P. P equals 17,000. What would the 3% be? The R, and how would we write it?
0.03.
0.03. And compounded annually, that gives us our N, and what would our N be? 1. Okay, so right now, that's all we're going to do is write the model using this information. So in these, instead of a Y and a T being left, there's going to be a capital A and a T left, okay? So we're going to have P, or capital A equals, the P is 17,000. What happens next?
1. In parentheses.
In parentheses, yeah, we got that 1 plus, but it's not just 1 plus R this time, what is it?
0.03 divided by 1.
Yeah, you gotta put the R over the N. So you have to take the rate and divide it by how many times it's going to be compounded, the N value. Well, this one happens to be 1. And then we have to do what with the T? Multiply it by the N. So we have to put a 1. Okay, so here we go. Let's get this cleaned up so we can say we have our model for this situation. Capital A, our Y value, stays capital A. 17,000. Well, what's 0.03 divided by 1? 0.03. And what's 1 plus 0.03? 1.03. And what's 1 times T? T. We'll just clean that up to T. Okay. This is our answer number 1, right here. Capital A left in it, little t left in it. No other variables anymore, and no other. Yeah. Because sometimes we are going to have to keep the N value there. It's just that it can be cleaned up in this situation. Is all.
You don't sub in the T right now.
Not right now. This is the model. This is the model that says if I want you to tell me how much money is gonna be in this account after 15 years, you could do it. If I sell somebody else, I want them to calculate how much will be in after 10 years, they can calculate it. If I tell somebody else I wanna know how much is in after 5 years, they can calculate it. So this model helps us do that. Then we use it to figure out how much money will be in there after 6 years. So A equals 17,000. I need you to write this out. Don't put it in your calculator till you do. Whoopsie. And the T will be replaced with 6. And this is money, so we're going to round to the nearest 100. So answer number 2. Devin, what you got?
2029.89.
2029. 0.8. So that'd be 80 cents. Okay. Should Devin stop and ask himself, does this seem reasonable?
No. Oh, I did it wrong.
Yeah, I was gonna say, there's a.
If it started with
There's
17,000.
another 8
there's
after
an
the
8.
9.
Yeah.
Oh, I was gonna say, if it started with 17,000, now it's down to 2,000, that's a problem, isn't it?
It's 20,290.
Oh, let's say.
Okay. Yeah, that seems like a little bit better. At least we made some money. That's good. So 20,000
Yeah,
and how much?
290.
200 how much?
98.
$98 and how much?
89 cents.
89 cents now?
Yeah.
Okay. Everybody agree with that one
Yes.
now?
Yeah.
Oh, good deal, made some money. Oh, I was afraid that this was gonna be like a place this person should not be investing their money. Okay, answer number 2. Okay, again, 2 answers. How many times I say that every year and students come back and don't get a paper stamp because here's what they would say their first answer is. This one right here. No. That model is already being used. They want the model that will work in any situation. So that is not your first answer. The circle black is the first answer. Okay. Let's do the next one. What's the 23,000?
P.
P. What's the 2%?
R.
R. What's the compounded quarterly?
4.
N equals 4. So now we can sub in and do our model. So the amount will be arrived at by starting with $23,000 investment, 1 plus the rate divided by 4, raised to the 4 times t power because the n has to be multiplied by the t, right? Okay, now all we got to do is clean that up. Make it a little bit more user-friendly, so somebody doesn't have to type quite so much in their calculator. So A equals 23,000. What does 0.2 divided by 4 become? 0.005, like half a penny. And then we add it to 1.
So 1.0.
Yeah, so 1.005, and it's to the 4t power. We can't clean that up. 4 times t is 4 times t. There's our first answer. Okay, now get the second answer. After 8 years, this is now our t value. And then when you're done, before you tell me what it is, will you make sure your answer makes sense? Should it be bigger or less than 23,000? Bigger, okay. Now again, you might want to be careful and not, if you're going to try and put this all in your calculator right now without simplifying 4 times 8, you got to know how to do that.
Oh, boy. Okay.
I would just probably take the time to do this.
Yeah, that's what I did.
Easier than trying to figure out how to put it in your calculator sometimes. Okay, this is still money. We're working with compound interest. How much money is in this account after 8 years?
26,900. Yeah, 79. .99.
You guys agree with Kat? Okay, so now I got it. There you go. So exponential growth, a special type of exponential growth called compound interest. And typically when you put money in a savings account at the bank, you're earning compounded interest, which is a good deal. That means you're earning interest on not only the original amount, but the money they keep giving you for free. You're also earning money on that. So you're earning free money on free money all the time. So you want to look for compound interest, not simple interest account. Okay? Okay, let's go to the last thing we're going to do, which is a special type of decay, and I want you to highlight this. A special type of exponential decay involves the half-life of substances. Where A is, again, the final amount. How much is there? So it's like our what? That capital A would be like our, okay, highlight this right there. That capital A would be like our what? In our y equals ax plus b. Our y. The capital P would be like our little a, okay, our lowercase a. And the 0.05 would be our b. They've already done the 1 minus. In other words, this is exponential decay. Remember, we have to take the rate away from 1. So they've already subtracted the rate away from 1, because what does half mean to you as a rate? What percentage is half? 50%. What's 50% as a decimal? 0.5. What's 1 take away 0.5? 0.5. They've already done the 1 minus the 50%, because it's, for this particular situation, it's half-life. It will always be 50%. So the 0.05 is our B, and what's the little t? X. It's like our X in our model. Okay, here's the other thing you might want to highlight, underline, whatever. This is important that you understand this. Students, this is where they'll do these wrong. T is the number of half-lives it goes through. So they give you the half-life, they give you the period of time. You have to figure out how many half-lives did it go through. Okay, so I want us right up here in this one. We're going to look at this example before we practice. This particular element, this whatever this is, this substance, has a half-life of approximately 60 seconds. Find the amount left from a 25-gram sample after 300 seconds. 300 is not our t-value. Notice what they did. They took the 300 and divided it by 60, because 60 is every 60 seconds, half of the substance is remaining. So I want you to write right here that this 5 is the number of half-lives it goes through. So how many times did it get cut in half? 5 times. In a 300-second period, there were 5 periods of 60 seconds, so it would be in half. Now, they already give the answer here, but I want us to just reason through that. If it starts at 28, how much is left after the first half-life? What's half of 28? 14, okay? If I'm just going to write this here so we know that we have, okay? So we have, after the first half-life, there's 14. Okay. How much would there be after it decays another half?
7.
7. Okay. How much would there be after it decays another half? 3.5. How much would it be if it decays another half? 1.75. Okay, might get to the point now you might need to use your calculator. And now it's got 1, 2, 3, 4. So 60 seconds, 120 seconds, 180 seconds, 240 seconds. It's got another half-life to go through. Point what?
875.
Really? Take 1.75 on your calculator and divide by 2.
2075.
0.875? Okay, well then, oh, that's, why was I doing 28? It should have been 25, my mistake, okay. So if we were actually doing this with the right number, then we would have gotten the right answer here. But do you understand what's actually happening? You just did, even though I misled you, you get the picture of what's actually going on here when we're using the formula? Okay, so let's try it now. We have a 30-gram sample. Okay, let's underline that. What's that in our formula? No?
P.
The starting amount, which in this one is
P.
P. This is capital P right here. P equals 30. It has a half-life of 8 days. Half-life of 8 days. So is N 8? No. No. So in these, there are two answers. There's only going to be one answer, really. Well, there's kind of two answers, but what we do is we have to say, we could start it like this. We could say, okay, we know we have a 30-gram sample. Here's what's going to happen. After you can tell me how many half-lives it's going to go through, I can tell you how much will be left of it. So this is kind of like the model for it. But now we have to find our t value. And what are we going to do to get our t value for this situation?
24 divided by 8.
24 has to be divided by the 8 to see how many half-lives it'll go through. So 8 days plus another 8 days is 16, plus another 8 days is 24. It's going to go through 3 half-lives. So now we can use our formula, replacing the t with 3, and see how many grams of this sample are left after 3 half-lives, after 24 days. How much is it?
3.7.
And what are they? Grams. 3.753 and 75 hundredths grams. So it's kind of like, this is our model for this one. The only thing that got replaced, that had to get replaced was the P because there is no R. It's already, the R is 0.5 and it's already been taken care of for us. So there's like our model, and the second answer is 3.75 grams. Okay, here's one thing that also you're going to be really, really careful of, just in case they do this to you. If the half-life is given, like this one is given in hours, but what if, instead of saying after 60 hours, they instead said after 2 days?
You convert the days to hours.
You have to make sure you convert the days to hours before you figure out how many half-lives it went through. So they have to be comparable. This one is in hours, and so is this one. So we don't have to do any changing of it. But we have to make sure that if the half-life is different than what they want us to, what it's going to go through, change that to what the half-life is measured in so that you're going to get a good answer. Okay, so what's the 40?
P.
P. Okay, let's write our model right away. A equals 40 times 0.5 raised to the t power. We don't have to think very hard for that one. So when you have a 40-gram sample of this sodium 24, you can figure out how much of it will be left given a time frame and knowing that the half-life is 15 hours. So what are we going to have to do?
Divide 60 by 50.
Divide 60 by 15, and how many half-lives did it go through? 4. Okay, now we'll use our model with a 4. Okay, I'm going to try this time to do this right. 40 after it goes through 1 half-life, it's got 20 grams left. 20 after it goes through another half-life has 10. 10 after it goes through another half-life has 5. 5 going through that last half-life would be 2.5. Am I right?
Yes.
Okay, 2.5, and these are measured in grams also. There's our second. Yes, Josh? Nope, that's just part of its name. That number is just part of its name. So. Okay, so you think you got this? Okay, let's get to work then. In your homework, you will have all of these different sorts of special exponential functions. And so make sure you are keeping your notes handy and using the appropriate formula for whatever type of problem it is.